Hello, I'm Erkan Tahiri and I'm going to present A2L, Anonymous Atomic Locks for Scalability Payment Channel Hubs. This is a joint work with Pedro Moreno Sanchez and Matteo Maffei. In this work, we construct scalable, secure, interoperable, and privacy-preserving payment based on trustless gateways, or so-called hubs. More precisely, we achieve the following four properties. Scalability, which means that our construction works over payment channels and therefore does not require any on-chain transactions. Atomicity, which means that no honest party loses any money. Unlinkability, which ensures that the gateway does not learn who is paying to whom. And interoperability, which means that the parties should be able to exchange coins between different cryptocurrencies, such as exchanging ethers for Bitcoin. Now we will look more closely into each of these properties. Cryptocurrencies inherently have a scalability issue, and payment channels have been proposed as a solution to this problem. They allow parties to perform arbitrarily many payments off-chain, while only two transactions, namely transactions for opening and closing the channel, go on-chain. However, it is financially prohibitive to open a payment channel with everyone. Hence, in practice, parties use gateway to route, or so-called payment channel hubs, to route their payments. How payment channel hubs work is that the sender, in this case Alice, forwards her coins to the gateway, and who in turn forwards them to the receiver, in this case Bob. However, it is easy to see that in such a scenario, a malicious gateway can steal the money of Alice. So this brings us to the security notion of interest in payment channel hubs, which is called atomicity. It basically means that both transactions should happen atomically, so either both of them succeed or both fail. The privacy notion of interest in payment channel hubs is called unlinkability. It essentially requires that the gateway should not learn who is paying to whom. More precisely, from a set of senders on the left and a set of receivers on the right, the gateway should not be able to link any particular pair of sender and receiver. The last property of interest in payment channel hubs is interoperability. Interoperability means that the payment channel hub construction should be backwards compatible with Bitcoin and as many cryptocurrencies as possible. It should be possible for parties to do exchanges across cryptocurrencies, such as in the example here, exchanging Bitcoins and Ethers. Payment channel hubs have been studied before, and state-of-the-art prior to our work was Tumbleweed. It is composed of two protocols, namely Puzzle Promise and Puzzle Solver. In order to solve the atomicity and unlinkability challenges, the authors of Tumbleweed suggested reversing the flow of payment. More precisely, assume we have Alice who wants to pay to Bob via the gateway, and gateway is in possession of certain secret information, here denoted with a blue key. What Tumbleweed does is that it allows the gateway to create a puzzle, denoted with the blue lock, such that Bob only gets paid by the gateway if he can find the solution to the puzzle, meaning if he can find the blue key. Since Bob does not know the key and he just wants to get paid, what he can do is that he can randomize the puzzle, here denoted with the green lock, and send it to Alice, who wants to make the payment. This part corresponds to the Puzzle Promise protocol of Tumbleweed. Next, Alice offers a payment to the gateway, conditioned on this randomized lock. Now, since gateway was the one who created the puzzle in the first place, it can solve the puzzle to obtain the randomized solution, denoted here with the green key. And lastly, use that to release the payment and get the coins of Alice. At this point, Alice can also obtain the solution to the randomized puzzle. As the last step, Alice shares the randomized solution with Bob, who can de-randomize it to obtain the original solution and release his payment that was previously promised by the gateway. This corresponds to the puzzle solver protocol of Tumbleweed. Although Tumbleweed achieves atomicity and unlinkability, it still has several drawbacks. More precisely, it lacks interoperability, while it only supports HTLC-based cryptocurrencies. This means that the puzzle, or the blue lock that was previously shown, is a hash value. Furthermore, the cut-and-choose proof technique that was used to prove the security of Tumbleweed causes large communication overhead, as the parties need to exchange many puzzles. Lastly, Tumbleweed is susceptible to griefing attacks. As was previously mentioned, in Tumbleweed, the gateway is the one that first locks coins during the Puzzle Promise protocol. Hence, one can perform a denial of service attack by asking the gateway for a large number of promises which later never get released, meaning for which there is no corresponding run of the puzzle solver protocol. This state of affairs leads us to consider the following question. Is it possible to design a payment channel hub that is efficient and that provides atomicity, unlinkability, and interoperability with virtually all cryptocurrencies? And we answer this question positively in our work. Before looking into our construction, we need to define certain cryptographic building blocks. The first of these is an adapter signature scheme that was previously defined by Aumeier et al. It essentially allows a party, in this case the gateway, to create an incomplete signature that Bob can only finish using certain secret value k. Moreover, if Bob finishes the signature, then the gateway can extract the secret value k. Let's look at it more closely. Assume that the gateway wants to pay one coin to Bob condition on the group element C, which is defined as k times the generator G here, for a group where the discrete logarithm problem is hard. Then the gateway can create an incomplete signature denoted here by sigma sub G over the transaction that pays money to Bob and share it with Bob. One can think of this procedure as the locking phase. Afterwards, Bob, using the secret value k, can turn the incomplete signature into a full valid signature, denoted here with sigma, and as was previously mentioned, this also allows the gateway to extract the secret value k. One can think of this as the release phase. Now we can attempt to construct a payment channel hub using adapter signatures. Similar to the flow in Tumbleweed, we start with the gateway and Bob executing the locking phase of the adapter signature on the condition C, defined as k times g. This essentially corresponds to the puzzle promise protocol. Next, Alex can execute the locking phase of adapter signature with the gateway, condition on the same value C that was previously used between the gateway and Bob. Now, since the gateway knows the secret value k, it can use it to finalize the incomplete signature of Alice to obtain a full valid signature and get paid by Alice. Due to the previously explained properties of adapter signatures, at this point, Alice can extract the secret value k using the full signature sigma and the incomplete signature sigma sub a. Lastly, Alice can share the value k with Bob, who can use it to complete the incomplete signature of the gateway and get paid by the gateway. And all this corresponds to the puzzle solver protocol. Now, if we look more closely into this construction, we can see that the same condition C is used during both protocol executions between gateway and Bob, and also between Alice and gateway. This basically breaks our notion of privacy, which is unlinkability, since the gateway sees the same k value on both sides, and it can trivially link the sender and receiver. The solution to this problem is to randomize the puzzle as is done in Tumbleweed. More precisely, looking back at the protocol of Tumbleweed, we see that the puzzle is randomized by Bob and given to Alice, who uses the randomized puzzle to initiate the interaction with the gateway. Hence, we follow the same protocol flow. However, recall that in our case, the puzzle is the condition of the adapter signature, which is a group element from a group where the discrete logarithm problem is hard. Therefore, randomizing the puzzle corresponds to computing a new group element, C prime, that is randomized with a random value R. But now the gateway cannot solve the puzzle since it does not know the randomization factor R that was used by Bob when randomizing the puzzle. The solution to this dilemma is to extend the puzzle with the encryption of the secret key under the gateway's key. This brings us to our second cryptographic building block called randomizable puzzle. It essentially combines the condition of adapter signature with an encryption under additively homomorphic encryption scheme. It allows the gateway to create a puzzle that can be solved using a trapdoor, which in this case will be the secret key of the encryption scheme. Moreover, the puzzle can be randomized to create a fresh-looking version. Let's look at this more closely. Here we assume that the gateway has public parameters, a trapdoor, and a secret value k, and Bob has a randomization factor R. Now, using the public parameters and the secret k, the gateway can create the puzzle pi, and Bob, using the randomization factor R, can create a randomized version of the puzzle denoted by pi prime here. This corresponds to puzzle generation and randomization. Next, Bob can share the randomized puzzle with the gateway, who can solve the puzzle using the trapdoor information to obtain the randomized solution R times K. However, since Bob has the randomization factor R, it can use it to de-randomize the solution and obtain the original secret value K. This corresponds to the puzzle solving and solution de-randomization phases. Now, combining adapter signature with randomizable puzzle, we can construct our A2L protocol. The construction starts with the gateway and Bob executing the puzzle promise protocol, from which an adapter signature sigma sub g and a randomizable puzzle pi is computed by the gateway, and a randomized puzzle pi prime is computed by Bob using the randomness r sub b. At this point, since Bob does not know the solution to the puzzle, he just shares the randomized puzzle pi prime with Alice. Next, Alice also randomizes the puzzle using her randomness R sub A in order to maintain her anonymity. Then computes an adapter signature under the conditions C double prime, where the condition can be extracted from the doubly randomized puzzle pi double prime. At this point, the gateway can solve the puzzle using his trapdoor to extract the solution R sub A times R sub B times K and use it to complete the adapter signature sigma sub A and get paid by Alice. Now, due to the properties of adapter signatures, Alice can extract the randomized solution from sigma. Alice removes her part of the randomness from the solution to obtain R sub B times K and shares it with Bob. Lastly, Bob can remove his part of the randomness from the solution he receives from Alice in order to obtain the secret value K that he needs to complete the adapter signature that he received by the gateway and get paid. We can see that now the conditions used are different. More precisely, Gateway and Bob uses C for the adapter signature computation, whereas Alice and Gateway uses C double prime. Moreover, we observe that the gateway only sees the randomized version of the secret value K, hence it cannot link Alice and Bob. In our work, we also describe a privacy-preserving registration protocol to protect the gateway against griefing attacks. I sketch here the high-level idea and refer you to our paper for the full details of our protocol. So essentially, our registration protocol is executed before the start of the puzzle promise between the gateway and Bob. It starts by Alice locking certain amount of coins for the gateway. This allows us to align the management of the collateral with the incentives of each party involved. After this, the gateway offers a randomizable token to Alice. Next, Alice randomizes the token and shares it with Bob. Lastly, Bob presents the randomized token to Gateway to initiate the puzzle promise protocol. The randomization allows to maintain the privacy of Alice and Bob. We also implemented A2L and measured its performance. We ran benchmarks both locally and over geographically distributed Amazon AWS machines. Our experimental results show that A2L incurs 33 times less bandwidth overhead compared to Tumbleweed and provides 2 times speed up in computation when using preprocessing. We highlight that in total, the execution time is about 300 milliseconds with a preprocessing technique, and it requires less than 10 kilobytes of communication in total. We refer to our paper for the complete performance evaluation. In conclusion, A2L is a cryptographic protocol for payment channel hub that achieves security, unlinkability, and interoperability. It is formally proven secure in the UC framework. It is backwards compatible with Bitcoin and scriptless cryptocurrencies such as Monero. It provides protection against griefing attacks, and it is currently existing most efficient Bitcoin compatible PCH. Our paper as well as implementations are available online. Thank you.